Hi, and welcome to the third lab. Today we'll talk about QuickSort and QuickSelect. QuickSort is a quick algorithm that sorts an array. Smushed. Yeah. Okay. So for this lab, the first step will be to implement QuickSort and measure how fast it is. Then we're gonna continue with QuickSelect. This one doesn't need any measurements, just the algorithm and testing if it works. Then we'll come back to QuickSort and compare it with heap sort, the one we did the previous lab. But the previous lab, we didn't measure how fast heap sort is. So that will be the step for grade 9. And finally, we need to find the best case and worst case for QuickSort and see their complexities. And last but not least, don't forget to check that they work, that the algorithm actually sorts the array for small cases. All right. Before we start talking about QuickSort, we need to talk about partition, which is the building block of QuickSort. So if you understand partition, QuickSort is easy. This is the hardest part. Basically, if you have one array with elements in any order, what we want to get is one of the elements somewhere in the center, and to the left we'll have smaller numbers, and to the right we'll have bigger numbers. Let's take an example. So let's say we have this array. We have small and big numbers, and what we want to get is that this last element is put somewhere in the middle, and to the left we have smaller numbers, and to the right we have bigger numbers. And this is useful because once we do this, we know that this element 10 is in the right place in the sorted array. So after we do this, we can just repeat this for the left part and right part, and finally we'll have a sorted array. This last element is called the pivot. It helps us, it's the number that gets in the center. It won't always get on position 3, like exactly in the middle of the array. It might get here or here, but the idea is to have the smaller to the left and bigger to the right. Now, how we do this in code? First, we pick the pivot, which is the last element. And after that, we consider a bar at the beginning, like here at the start of the array. And in the end, we will have small numbers to the left of the bar and bigger numbers to the right of the bar. Well, we'll see, it's not that fancy. So basically, we'll take each element and compare it with the pivot. If the current element is bigger, we don't do anything, we do nothing. Now, let's move on to the next one. Well, this one is smaller than the 10. And in that case, we swap the current element with the element that's next to the bar. And then we move the bar. So this, since 6 is smaller than 10, we want it to be to the left of the bar. Now, 12 is like the same, it's bigger, so we skip it. When we get to the 3, we move the bar to the right and move the 3 behind it. So it becomes something like this. And we go on to 19, which is bigger, we don't do anything. And when we get to the 9, we swap. So this is very important. If the number is bigger than the pivot, we don't do anything. If it's smaller, move the bar to the right and swap. Now, at this point, we have smaller numbers here. We have bigger numbers here, but we don't have the pivot here in the middle. So the last step is just swapping the pivot with the element after the bar. So it becomes like this. And now it looks good. That's what partition does. It puts the pivot in the right position. And also smaller to the left and bigger to the right. Now you go ahead and try it. Here is another array and see what the partition function would do with this one. Start with the pivot 5 and take each step and see how it works. You can put this on pause and I'll keep going. Okay, I hope you did it. I have no idea how it looks like, but I trust you. I think it's okay. If you have any questions, don't forget to send me a message or something on Teams or email or whatever works for you. All right. Now let's see how it looks in code. So here is the array we're trying to sort. Here we have the pseudocode for this function. And here we'll see each variable, what value it has at this point. So we have this P and R. These are the start index and the end index, left and right. These tell us which part of the array we want to partition. For now, they will always be 0, left will be 0, and right will be the last one, so it will be 6. Now, the first thing, as we discussed before, is taking the pivot. We use the variable x to denote the pivot, so x is 5. Then we use I, which is the bar index. In the beginning, it is -1. It is to the left of the first element. That's why it's p -1. And then we take each element from 0 until 5. And if it's smaller, we do something. But here, 9 is bigger, so we don't do anything. We move on to 7, which is bigger, we don't do anything. Then we move to 3. 3 is smaller than 5. So we move the bar to the right. I becomes 0. It's here. And we exchange the current element with what's left to the bar. And we go and go and go on until we reach the last element. And at that point, we exchange the first element after the bar. So if the bar is at position 2, we exchange the pivot with position 3. Okay. And the last step is to return this index, the index after the bar, because in QuickSort, we will want to do something with the left part and with the right part. So we need the index to know how to split the array. Okay, so the first task is to write the partition function using this pseudocode. And then in the main function, create an array that looks like this and call the partition function and show the partitioned array. Please check that 5 is somewhere in the middle. It should look like this in the end. Now go ahead, put the pause in here and try to write the function. All right. Let's see what's next. So now that you have the partition function, we're ready to implement QuickSort. The basic idea is simple. There are 3 steps. First, we partition. We do what we did before. And then we call QuickSort on the left side and QuickSort on the right side. So basically, we repeat the thing on the left part, and let's see how it looks. So let's say we have this array. First, we partition. We put the 10 where it belongs, and we'll have smaller to the left, bigger to the right. Then we'll only consider the left side and try to sort this part. Again, we partition. Here, we don't have, both of them are smaller, so the bar will keep moving. And then the 9 will swap with itself. It's kind of a corner case here, but it doesn't matter. Partition will work. So we see that the 9 is placed in the correct position, and 6 and 3 are smaller. So we started with QuickSort on the big array. We started the left part, and we did the partition. And after that, we do QuickSort on the left side. And again, we do partition. We take each number. Here, we don't move the bar because it's bigger, and we finally swap. Now the pivot is in the correct position, and we're done. And on the right side, it will be the same. As you see, now the left side is completely sorted. We only need to take care of this. All right. So the pseudocode for QuickSort is quite short. First, we check if the left index is smaller than the right index. Basically, if we get to an array of size 1, we don't need to do anything. But otherwise, we partition the array and see where the pivot got to. And then we quicksort with left and pivot -1, and quicksort with pivot +1 and right. And can you try to guess which one is the left side and which one is to the right side? I think it's this one to the left side, because here, yeah, we go to the left of the pivot, and here we go to the right of the pivot. Right. And the next step is for you to write the quicksort function and to test it in the main function. Instead of partition, just call quicksort and it should be okay. Now you should expect that the array is sorted, not only the pivot is in the right position. All right, go ahead and pause and then we'll come back. Okay, I hope it went well, and if it didn't, don't hesitate to tell me. All right. Now, let's talk a little bit about the best and worst case for quicksort. I think there's too much color on this slide, but anyways, the best case happens when the pivot always gets to the middle. So basically, if the last element is perfectly in the center, and then again, the pivot gets in the center even on the left side and right side, and then again, basically, if it always splits the array in two equal parts or almost equal, then it's a good case. It's the best case, because here for each partition, here we do n operations. To partition, the partition is O of n, it's linear. The next time we partition 1/2 with half of n operations, and the other half again with n/2 operations. And in total, we'll have n operations. And here, when we do these small bits, again, we'll have n/4, 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 n/4. So basically, we again have n operations in total. And if we keep dividing, we'll have like log of n levels. So this is level 1, level 2, level 3. And if we go on, it will be more smaller. I mean, more small arrays, but they get smaller. So anyways, the complexity should be n log n in the best case, but in the worst case, this is quite bad. If the pivot always is the first or the last element, I mean the biggest or the smallest element, like in a sorted array, here for the first pivot, we do n operations. The second time, we'll do n-1. The third time, we'll do n-2 operations, and so on. And if we compute this sum, we'll get to n² operations, about n². So basically, it is bad if the pivot doesn't split the array into equal parts. And it's very good if the pivot always splits the array into equal parts. Now, in case you want to avoid this case, this kind of a hack. Instead of using the partition function, use randomized partition function, which basically doesn't always choose the last element as the pivot, but takes one random element and swaps the two of them. So at each point, you will have a random pivot. That doesn't mean that there won't be a worst case. I mean, if you're very, very unlucky, the random will be very bad. But in general, there are very small chances that you will get in the worst case with a random pivot. But this is optional. You don't have to implement it. You can just ignore it. Okay. Now, for the worst case, it's really easy to generate an array. That's like at each index, it's just the same number. But for the best case, it's a little bit trickier. Here we have a pseudocode. So if we always want the center to be the pivot, we should just start with an array sorted, a sorted array, and swap the middle with the last one. So then the pivot will be at the end, the right element. But the problem is that if we do this, the left side and the right side, they will be worst case scenarios. So only the first partition will be successful. And to avoid that, we can do a recursive function that first fixes the left part, then fixes the right part, and only after that we move the center to the last. So here we go to the left side and put the right pivot. Then we go to the right part and put the right pivot. And then we put the right pivot to the big array. So the code would look like this. If we have at least two elements, we take the middle, we fix the left part, we fix the right part, and then we swap the center with the last one. I mean, here, after we fixed left and right. All right. All right. And the last part is the QuickSelect algorithm. This one is a bit tricky. It doesn't sort. It doesn't do what we're used to. This is a new task. We haven't seen this before. So basically what select means is when we have an array, select of 1 will give us the smallest element, which is 2. Select of the array and 2 will give us the second smallest element, which is 3. If we do select of an array and 5 will return the fifth smallest element. So this is first, second, third, fourth, and fifth. So it's 7. And if we do it with 3, it's the third one. So it's 4. What happens if we do quick select of this array and 4? What should it return? So it's 1, 2, 3, 4. Yeah, it should give us 5. I hope it makes sense what we are trying to do. And one way of doing it is by also using the partition function. Now, let's say we have this array and we want to find the fifth smallest one. What we will do is do a partition. Let's see. So 9 is bigger, 7 is bigger, 3 is smaller, so we move the bar, and we swap with 9. Then we get to the 2, it's smaller, so we swap. And 7. 6 is bigger, we don't do anything. 4 is smaller, we move the bar and swap. And 9. And now we go to the end and we can swap the pivot with the middle. All right. So we've done a partition. Now we're looking for the fifth smallest element. Will it be on the left or on the right? Well, since the fourth number is smaller. I mean, if we know that this 5 is on position 4, on position 3 in the array, it's clear that we need to look into the right side. Then we go to the right side and do a partition again. Start. Sorry. So we choose the pivot, take the bar, and each element, we look. Is it smaller? If so, we swap and move the bar. This one is bigger, so we don't need to do anything. And we're at the end of the array, so we swap like this. Now, this was the pivot. This is not. And now we look at the position. So we have the pivot at position 5, and we're looking at the fifth smallest element. Now, this might be the one, but we're indexing from 0, and I is numbering from 1. So it's still not this one. We need to look to the left. And at this point, we have only one element here, so we can be sure that this one is the right element. So this will return 6. The algorithm looks like this. So if we want to select from the array from left to right, the position I, the I smallest one, first we check, sorry, here I should have put P and R. If we only have one element remaining, we're sure that that one is the result. Otherwise, we partition and see if the pivot is exactly at that position. That means that we found the ith smallest element and just return it. But otherwise, if the element, the ith smallest element is to the left of the pivot, we go and select the left. So from P to Q minus 1. But if it's greater, then we select from Q plus 1 to right. So we go to the right side. So we have 3 cases. The pivot is the element we're looking for. The pivot is on the element we're looking for is to the left of the pivot. And the element we're looking for is to the right of the pivot. So now try to write this function and test that it works correctly, I don't know, with these small examples. And if it returns the right number, then we're all good. If it doesn't, just let me know and we'll look into it. After you do this quick select, you just to recap. So we've done the quick sort and the quick select. The next step I would do is to count the operations of QuickSort. Use the OP++ there wherever you use the array. In QuickSort and also partition. And do some plots either in Excel or with the profiler. And we only need the average case at first. And again, take 5 samples, so don't test only once for n. And you need to count the operations together, so you don't need assignments and comparisons separately. Just put them in the same variable. After that, do the quick select. Then count the operations of heap sort. I think you already count the bottom up and min max heapify. So you'll only need to count operations of heap sorts from the previous lab. And after that, compare QuickSort with heap sort using the average case plots and say which one is better and the complexity of each one. And finally, try to implement this best case and worst case as seen here and here. This is the best case, and the worst case is just this one, and measure how fast they are. You should see n log n for best case and n squared for the worst case. And yeah, I think that's all. So in the end, I want to see 3 plots, one for quicksort versus heap sort. So it should be a graph with 2 lines, and one for quicksort best case. So one plot with 1 line, and one for the worst case, one plot with 1 line. And in the end, don't forget to put a comment with the complexity for quicksort and heap sort in the average case, and quicksort on the best and worst case. So there should be 4 complexities. And good luck, and let me know if there's any way I can help. See ya.